Hi, this is Youness SAAIDI here, and we are going to go over a problem that deals with calculating economic order quantity as well as the reorder point policy. So let's go right through it. And the problem says that we have to import electronic machines from Japan. And to do so, the freight company is proposing two types of shipping containers. They have 20-foot and 40-foot containers, which have respectively the capacity to ship 1,000 and 2,000 electronic machines. And they give us some of the inputs. We have, for example, the annual constant sales are estimated to be 12,000 machines per year, and the cost price from Japan port is $100 per machine, while the transportation cost for a container delivered to our warehouse equals to 150 plus 30 times X. The X is for the type of corresponds to the type of container. And finally, the annual holding cost is 18%. And just so you know, for those who are studying or interested in international trade, this is a type of commercial transaction where most of companies would use the FOB Incoterm, which means free on board, which states that the supplier delivers when the goods pass the ship's rail at the agreed port of shipment. From that point, we'll have mainly to pay and bear all costs and risks. So every time you see a problem or you have to deal with such operation where you have to pay the most of costs from a certain port, just keep in mind that this might be a FOB Incoterm. That being said, let's go back to our problem. So the questions we will be answering are, first question is, which container presents the best optimal costs to supply the electronic machines? What is the supply frequency and the procurement total cost? The second question says that with specified containers of 10, 30 or 50 foot, with an overcosts of $300 per year and per container, and for a turnover of 1 delivery per month, would we change our initial choice? If so, what is it in terms of supply frequency, quantity, and costs? The third one says that if we adopt a reorder point policy and statistical analysis shows that the weekly demand is modeled through Gauss's law, for which the average demand is 250 electronic machines and a standard deviation of 100 machine, if you want to limit the probability of rupture by 2%, what would be the value of rope, knowing that the lead time is 2 weeks? So in order to answer the first question, we must understand how much we are paying for each of the container. So without further ado, let's open a spreadsheet in Microsoft Excel. To compile these costs and variables, I've copied some of the data and I've used the notations which correspond to the formula. So once again, we sell 12,000 of these machines in a year. The cost price we pay from the port is $100 per each item. Now for the costs related to transportation, we need to underline here that in terms of logistics, when we talk about transportation costs, we are always going to have that expression of costs or cost structure. And in our next video, we are going to see how is it possible for a company or for a logistics manager, how is it possible to express the transportation costs into that structure? Because it is very important to know how much exactly a one single delivery costs, taking into consideration all of the expenses related to transportations. Then we have a holding cost of 18%. So usually we will find that the holding cost is a certain percentage. And to get this holding cost, we will simply take that rate and multiply it by the price. So here we have laid down some of the calculations we need to go through regarding each type of the container in order to get this procurement total cost. Now for the supply frequency, in order to get this supply frequency, we will simply divide the annual sales, which is 12,000 units, by the shipping capacity of the corresponding container, and that will give us 12 times, which means that we are going to supply our warehouse 12 times in a year. I will delete these automatic calculations. For the average inventory, normally the average inventory is calculated through the formula of current inventory plus previous inventory divided by 2. But for this case, as the average inventory is related to our ordering quantity, because basically we are going to order a maximum of 1000 units, and as the maximum amount of inventory we are going to have at any time is 1000 units, and the least amount of inventory will be 0, the average inventory represents that halfway cycle. So we are going to divide 1000 units by 2 to know where the halfway is. Then we will say that the average inventory between our maximum and minimum, the highest possible being 1000 units, and where 0 is the minimum, the average inventory would be 1000 units divided by 2, and that will give us 500 items. And now for the fixed cost of annual transportation, this will equal to 150 times the supply frequency. That will give us $1,800. For the variable one, it will be 30 times the corresponding container, which is 20 times the supply frequency, which equals to $7,200. The total cost of transportation will be simply the sum of these two costs. Which is $9,000. Now, in order to include the transportation cost to the cost price, which we already have here, which is $100 that we pay from the port of Japan, we will simply take the total cost of transportation that we have here, divided by the shipping quantity to know how much it costs us for each item. And I'm going to make this in brackets. Divided by the supply frequency plus the cost price from Japan, which is $100. And that will give us $100.75. For the annual holding costs, this is very important. As I've explained previously, we are usually going to find that the annual holding cost is expressed through a certain percentage. So to get this annual holding cost, we will simply take this percentage, multiply it by the cost that we pay from the port, and multiply it also by the average inventory, and this will give us $9,000. So I'm going to duplicate the same calculations into the container, into the 40 foot container, and I am going to get back to you. So now that we have been going through these calculations, it is obvious that the small containers are very economic when we compare the total cost of procurement, as we have to pay $18,000 for the 20-foot container versus $26,000 for 40-foot container. So we are going basically to go with the first container of 20 foot. Now, coming to the economic order quantity calculation, I've made a screenshot of the formula, And in order to make the calculations easy, we are going to multiply it in different cells to make sure that it does it correctly. So the first thing we are going to do, we are going to calculate the top part of the equation, and we have economic order quantity equals to square root of 2 times D times S divided by H. So the top part of the equation would be 2 times D, which is our annual demand, times our ordering costs of 150. And we are not going to take into consideration the variable cost of the transportation, as the quantity or the ordering cost does not depend on these variable aspects. So the top part would be divided by our H, and our H would be the annual holding cost, H in percent, times $100, which is our cost price. Now I am going to call up the function of square root in Excel and divide the top part of the equation by our H, and that will give us 447. So I am going to run up this. And that will give us a economic order quantity of 447. Now for the second question, where the freight company proposes other container types amongst their arsenal. So they are basically proposing other containers of 10, 30, or 50 foot. But right off the bat, we notice that based on our previous calculations, that choosing a container of more than 20 foot is a nonsense, as the optimum solution corresponds to a container of 10 foot for Q equals to 447 items. Then, following the current figures given to us, and in order to confirm this choice, we need to make sure that the overcost related to the specified container is not going to penalize our overall costs. For that, we need, of course, first to calculate the transportation costs, to which we are going to add the holding cost, then the overcost of $300 per container and per year. So the transportation costs would be 24, which is the supply frequency, as 12,000 items divided by 500 items, which is the shipping capacity of the container, equals to 24. So times the whole transportation cost expression, which is 150 plus 30 times 10, which gives us a cost of transportation of $10,800. So the same goes for the holding costs, where we have the average inventory times the cost price times the holding cost, expressed as a percentage. So we have 500 divided by 2 is 250, which is our average inventory. So 250 times 100.9 times 18%, and that will give us 4,540. But if we add the specified overcost of $300 per year and per container, then we will say that in order to supply the 12,000 machines, the supply frequency would be 24 deliveries. And if the turnover takes 1 month, then the number of containers needed is going to be 24 divided by 12, which gives us 2 containers. The overcost being $600 for $300 times 2 per year, and that results to a total cost of procurement of $15,940. We then conclude that it is more interesting from an economical perspective to boost the supply frequency up to 24 times instead of 12 times per year with a 10-foot container to supply 500 electronic machines. The bottom line in procurement matters is that as the frequency of supply increases, the holding cost decreases, and vice versa. If we are holding a considerable amount of inventory in our warehouse with less supply frequency, then the holding cost is going to be more expensive. So that's a correlated rule to know and to keep in mind when it comes to inventory management. Now, heading for the last question about the reorder point policy. So the level of inventory we need to maintain in order to meet the demand within 2 weeks, considering a probability of rupture of 2%. So once again, I've made a screenshot of the formula of the reorder point policy as we have seen in our previous video. Then, if we suppose that we are capable of handling or withstanding the probability of rupture of 2%, which means heading for a quality of service of 98%, we would then call up the function to know the safety factor. To do so, we are going to type this nice feature in Excel of norm as inverse, the normal statistical inverse. It will calculate the inverse normal cumulative distribution for a given probability value. So we will say that safety factor equals to, and we are going to type the formula equals to norm dot inverse dot s dot inverse, and we are going to select the probability, and that will give us a safety factor of 2.05. Then the lead time demand would be 250 times the 2 weeks that we need to meet in terms of demand, which will give us 500. So in order to get this reorder point policy, we are either going to calculate this manually 40, and we will say that reorder point policy equals to lead time demand, which is 500, plus the safety stock being our safety factor times the standard deviation, which is 141, and that will give us 790 item. Or we can go to Formula tab in Microsoft Excel, click on More Functions, Statistical, and go to norm.inverse. I'm going to select this. Let me see. So this is norm inverse, and here we are going to simply select our input. So we have the probability is 98%. The mean is simply the lead time demand, which is 500, and the standard deviation is 149. So, and that will give us also 790. And here we have the whole problem done. We have a 24 procurement cycles in which we are confident to deliver at a rate of 98%. And each time the inventory reaches a quantity of 790 items, we are going to order a container of 10 foot, which corresponds, by the way, to our economic order quantity of 447. That's it. Thank you, and see you in the next video.